Our next speaker will be Oriol Vinyals from Google AI, who will speak about the state of deep reinforcement learning.
Sure. Thank you. All right, thanks. So perhaps a bit different from deep learning, and just given the recent maybe 3 years of research, deep reinforcement learning is emerging as perhaps the next deep learning, so to speak. It's really a subfield of deep learning in a way, but you can see a lot of activity, workshops being organized in the machine learning conferences, and a lot of new problems being tackled or trying to be tackled by these sort of techniques. So I wanted to give maybe an overview on what is deep reinforcement learning about, give you some intuitions and some examples, and obviously also posing some hard questions to understand the science of deep reinforcement learning, which would be even more challenging, as you will see, as to explain, as opposed to what the science of deep learning might require us to understand. So the first part, I would like to just briefly describe what's deep reinforcement learning really. And at this point, you understand that deep learning is mostly or largely in part about supervised learning, where the source of knowledge comes from a data set, a training data set, where you try to mimic some sort of input-output mapping, and you do that by optimizing some complicated nonlinear function. And this can be about classification or language understanding, emotion recognition, and all sorts of different things. And it has this very kind of interesting paradigm where the problem and the benchmark is set up by defining a training set and then a test set. And I really like a talk by Leon, who I think is in the audience, some years ago, who said that this paradigm of training and test split should start to disappear as we make more progress towards artificial intelligence. So really, the paradigm, or sort of the pictorial representation of deep reinforcement learning, is the following. You don't have a data set. What you have is an environment. This environment provides you with observations, and there's an agent. This could be even like rule-based systems or obviously deep neural networks, as you will see in a second. This agent observes these observations given to it by the environment, and then it produces an action so as to achieve some goal that the agent is after. And obviously this feels very general. It's a very general approach. The first talk about self-driving cars, well, then the environment would be a car, and the objective would be to go to, let's say, New York City without minimizing your time and so on and so forth, but with minimizing your risk as well. Environments could also even be a supervised learning data set where it's giving you images and your task would be to predict their correct class, although that would not be a very wise way to do supervised learning, given the noise and the variance added by the process of the agent, which actually has to propose the solution as opposed to being given to it by a label. So let's look at why or how it all started, at least from my own, in my career when I was there was this very interesting deep learning workshop at NeurIPS in 2014. It was interesting for several reasons, one of which was actually that Mark Zuckerberg attended, and he kind of announced that FAIR, the Facebook AI Research Lab, was going to be open. But perhaps more importantly, Vlad presented this very cool work in which he was able, or they were able at DeepMind, they were able to train a deep neural network that just via the principles I described was able to maximize the scores on a variety of Atari games, which is obviously a reasonably simple environment, yet we as humans have played many hours of Atari and found it reasonably entertaining to spend, again, a cumulative amount of time as a society. And what was very interesting about the approach was that it was very, let's call it deep learning-like. It looked at as the input were literally the raw pixels, and then the actions were which button are you going to smash next, basically. And that really worked. It produced very good kind of human-level performance on all these Atari games. And ever since then, this has been one of the benchmarks in kind of measuring these agents that do play in several environments. But also, as Jitendra mentioned, this is a fairly simplified domain, right? It's not, I mean, it has imperfect information. The number of actions you can perform is very limited. They're very simplistic. Moving left or right in the real world takes a lot of skills, motor skills, visual perception, and so on. So obviously, this is a huge simplification of a very kind of hard problem, which would be the environment being the real world. And what I like to think about is this idea that behind a great agent, you must kind of challenge it with a great environment, much like to extract very interesting rules in a supervised deep learning system, you must have an interesting data set to train on. And I don't think that is necessarily bad that Atari is so simplistic. In fact, I see many parallels with things like MNIST, which was not very realistically looking images. It was very simple task to classify 10 digits and so on. Yet, progress was able to be measured, and eventually it led to ImageNet and beyond. Obviously, vision is a field that is not going to be solved for many years, I believe. So, as a result, the community working on reinforcement learning and deep reinforcement learning has come up with a variety of benchmarks of increasing or different levels of skills required to solve, just to test, develop, and eventually do science on these new kind of recent techniques that are being proposed in the sense of deep reinforcement learning. And to be concrete, I'm not going to read through the pseudocode, although this is actually a fairly simple algorithm, but I'm going to try to explain you at a high level how do these agents optimize what they are after. And in here, you will see already a bit of the difficulties involved. So the way that deep reinforcement learning works, there's several algorithms, but one that's fairly popular, it's one where there's an agent here that is looking at several observations over time. Imagine this is a chessboard that you observed every time step, and you're going to act on it with pi, or in this case, maybe given the arrows, let's imagine this is an Atari game where you can go up, up, down, left, right. So the agent at each time step t is going to have to decide first what action to perform, that's pi, the policy. But then also, the problem is if you sort of look at maybe 10 or 5 time steps of a game, you might not see any reward, right? This game might really be about surviving as long as possible. So you don't want to be rolling out the full game until completion, and you're going to try to truncate this, much like you truncate language modeling and so on, as it was explained before. But then the problem is there's no reward. You're just playing, and you don't know whether you're winning or losing. So that's where the V, the value function, comes up. And this V is, again, a model that the policy must output. It's a scalar, generally, that tells you the probability of winning given the current state and of winning eventually, if you roll out where to play out the whole episode. And in this example, what you see is the value here is maybe around 50%, and eventually something good maybe happens, or the policy network thinks that, the value network rather thinks that something good is going on, and the value increases to 1. The probability of winning becomes 1. So the way these algorithms generate gradients for the policy, for the actions to issue, is that, well, they issued this random sequence of actions, but then obviously their prediction was there was 50% chance of winning, and eventually it got better. So then all the actions that led to the being better, being in a better state in probability 1 of winning, all these actions, this gap, produce gradients that reinforce the actions taken on those first 3 time steps over there. And then later on, you were winning already, so the actions basically become less relevant. But this obviously has a huge problem, which is, what if the value network was wrong? What if you reinforce those actions with green, you say, do more of these, that seem to be leading to a good spot in state space. But imagine eventually you actually lose. You play the game and you lost the game of chess, or in Atari, you were eaten by an alien or something. Well, you already updated the policy, but you updated it with the wrong information. But really what went wrong in this example is that the value network was not accurate. It thought you were going to win, but eventually you lost. So you're training both not only the arrows, the policy, the actions, but you're also training the value. In this case, this episode will tell you you were not correct at estimating that you are going to win. And as a result, I'm going to also teach you what it means to win or not. And this goes on and on as you train this reinforcement learning process. And obviously, that creates a huge amount of uncertainty in that the value network needs to be good, the policy network needs to also kind of adapt quickly to the environment. And as a result, the loss that we're optimizing becomes non-stationary, which is actually quite a big challenge in reinforcement learning. So let's look at how these two components, the policy and the value, came about in the first case study that I wanted to explain. I'm not going to explain this in many detail, but I hope to give you an intuition on how these things work. So the first study is AlphaGo and AlphaZero. As we know, environments that have been great challenges for humanity in terms of challenging their intellect, creativity, chess was one of them, and it certainly is quite complex, but Go, in terms of branching factor and depth, was a step forward. And as a result, it was believed, well, maybe we need a bit more compute power for search, which is such a good fit for these kind of games, to work well. And indeed, comparing to Atari, we already see some interesting properties of Go, and of course of chess as well, which were not present there. Namely, it is multiplayer, so the game is as difficult as your opponent is. It's almost unbounded, the difficulty, unless you know the full search space and you play the perfect move, which is certainly possible, although computationally not very feasible. And also the action space in Go is quite much harder because you have these 19 by 19 locations where you can place your stone. So it's obviously poses some extra challenges that Atari didn't pose. So this would be the next maybe data set. It's maybe Caltech 101 or so. And the way it works is really by exploring a very interesting source of knowledge, which is humans have played this game for a while. And we actually have recorded a data set, essentially, a supervised data set of human moves, and obviously of who eventually end up winning the game, many games of Go that are recorded for historical purposes. So then what you can do is simply train the policy network to predict the moves that humans did, and likewise the value network to predict in this position who is actually going to eventually win, which is very hard to make rules of. Unlike in chess, where maybe having a queen is a big deal and so on, in Go it's actually quite difficult to handcraft features to decide who is ahead. And with these two components, plus then now here comes classical AI, which I think that was the most beautiful part of AlphaGo. With search, plus these two components with deep learning, essentially, you created an agent that was able to perform really well at Go by doing the following trick, which obviously in hindsight is very obvious. Instead of doing exhaustive search of all the possibilities in the game, what you're going to do is prune the breadth. So you're not going to explore absolutely every move. You just want to explore moves that look likely under the policy trained on human data. So if a human would never place a stone there, you don't even need to expand that area of the search tree. And similarly, you want to cut depth. You don't want to roll out a Go game which might go for hundreds of moves, maybe 150 or so on, to the end, to completion, because that's expensive. At some point, you will use the value network to tell you when it's already very clear what's the probability that player 1 or player 2 is going to win. And these two components were critical then for developing what was called AlphaGo, and it was performing really well against people who are really good at the game, who really studied the game. And this game obviously has been around for a while. So in terms of challenging human intellect, that was a pretty nice result that we all liked. And then there's a twist to it, which is we started from the human data, which is actually, I think it's a very nice thing. But on the other hand, is there something a bit more from principles that we could use to train a Go algorithm that will not even use or know how to play Go at all? It's going to start playing literally random moves, which sounds a bit crazy, but actually in Atari, that's exactly how it goes. You first try to move randomly, eventually you get some rewards, and you reinforce those behaviors and so on and so forth. And it turns out that in Go, there's a very critical component that was not removed, which is the search component. And with search, it turns out that the state of the art before AlphaGo was actually a search algorithm based on MCTS. And that is so elegant, because what you can then do is take a random policy, which is essentially amounts to say, I don't know exactly which branches to explore, and I have no clue who is ahead, but I know that search will make my policy a bit better. My random policy is going to improve. And then thanks to something called the theorem, the policy improvement theorem, what you did is, okay, I take my random policy, I'm going to play against myself a full game. It's going to look not a great game of Go, by the way. It's a random game, literally. But it's going to eventually finish, hopefully. And then what I'm going to do is I'm going to try to imitate the move that I did after the search. So you take the random policy, you improve that move with search, and then you try to imitate. So you're creating, in a way, a supervised data set of better moves than the ones that you know about. And very similarly for the value network, or who is going to win, again, you look at the end of the game, and you also try to then understand, well, throughout the whole game, maybe black seem to be ahead, and so you backpropagate on the value network that fact. And this, actually, the whole thing, eventually leads to policies and values that keep improving enough that yielded essentially a program that, without this initial bootstrap from human knowledge, was able to also perform really, really well. And in terms of ELO score, which is the metric of performance in Go, it was kind of outperforming AlphaGo and so on. So even without the human help, so to speak, it was able to really become a very good Go player. And that was kind of the success story that you probably have heard several times about AlphaGo and Go in general. And then just a note on compute. It is true that it requires a lot of compute to develop, imagine, from scratch Go to actually playing Go very well, because we're not utilizing anything about evolution or about any intuitions that we come sort of, or we learn throughout our lifetime experience, and we learned as in kind of culturally as well. But at the very least, to run, once you train the model, to run the model, it's not as expensive as you might think. You don't need a big data center. In fact, maybe one of the more modern TPUs, these are not the latest ones, could run on your machine, and you could actually be playing Go with a reasonable amount of compute. But of course, the training would take more compute indeed. Second case study that I wanted to discuss goes a little beyond AlphaGo in certain, of Go in certain aspects, which is a real-time strategy game called StarCraft. Now, StarCraft is, I cannot describe the game, although I would love to, but essentially, let me try to map it to chess, okay? So imagine chess, where you don't see the opponent, and you start with very few pieces, and you have to decide whether you will build new pieces and which kind of pieces are you going to build, but you don't know, you don't see all the time what the opponent is doing. And at the same time, you can collect resources from the board, but collecting resources will make you weaker, will make your defenses weaker, so you must trade off sort of economical aspects, and there's all sorts of complexities involved in playing real-time strategy games, and StarCraft is one of the most popular ones. These are some images here. So in terms of benchmarking, now we reach a game that has imperfect information. We don't know what the opponent is doing at all times, unlike Go, chess, or Atari. And the action space is really much larger than both Atari and Go. In fact, to play this game, you must click in the screen. It's a bit like a drag and drop or point and click interface, right? So it's really a very modern game, and it requires quite a few more actions, and depends how you compute them, but certainly millions of actions, which makes certain problems quite more difficult. And luckily, there's been a nice history about StarCraft being used for AI development. And funnily enough, I was at Berkeley in 2010 when Dan Klein organized a team that built a rule-based bot to play the game, which, by the way, didn't work very well. And as a result, he was motivated to teach students about AI through the lens of a video game, which obviously is quite motivating for students. And he had this one slide, which this was from 2011, that it basically mentioned that no single AI technique can solve StarCraft, a problem of StarCraft off the shelf. And what we're trying here is to precisely do that. We're trying to literally learn a neural network that will play the game as well as possible without needing to solve all these sub-problems about search, pathing, planning, and so on that are required to play this game. So how did it work out? And it really didn't, I'm not sure the video will play, maybe not. Let's see. Let's try again. I mean, if you don't know about the game, maybe you don't understand, but it's, can we try to play the video? Yes, thank you. So when you try self-play, if the video plays, if not, it's going to be fine. Let's see. I saw a mouse moving. If you click the play button, maybe. All right. So in this video, what you show, yeah, this next slide, it didn't work. Well, if the video shows, what you would see is that the strategy that you learn is pick all your workers and attack the enemy base without regards of building anything new. So the problem is exploration is really, really hard. And a random agent, a really random agent, is going to take these workers that start mining minerals, this resource, and really just send them around the map randomly, which is not a great way to learn the game. But if you ask a random algorithm or a random policy to do that, you're going to really, really struggle to learn anything. I don't know. Yeah, that looks like the right button to click. All right. This is see the reinforcement learning. I'm not sure it's going to work. OK, never mind. So let's go to the next slide. So this policy was not very good. It was not even worth to test against humans. However, it beat all the bots that Blizzard has put in the game, from the very easy to one that's called Cheat Insane that is pretty difficult to beat. And it really was able to exploit certain issues with the rule-based system that Blizzard has placed in the bots, which did not react very properly to defend with its own workers when it saw all the workers coming in to attack. So what we decided to do is there's a large amount of human data that Blizzard very graciously open sourced for anyone to download of people playing the game. Which they do online at scale. And the idea was, well, can we actually learn to play this game much like we maybe learned to play Go, although this is slightly more complex because memory is required and so on and so forth. And the very cool thing here is that I worked a lot on things like natural language processing and translation, which was mentioned by Chris in the previous talk. And exactly the same architectures that are so good at predicting the next word were extremely good as well as playing this game. So essentially, you can think of, given all the observations up to time t, and all the actions that I performed into the game up to time t, I'm just going to simply try to predict what's the next action going to be. And that alone actually yielded a very nice, oh, we see the video here, a very nice agent that doesn't know what winning is. It's just really trying to learn StarCraft as if it was a language. And you see it moving the camera around, building new units, getting this clump of units moving down where the enemy would be to engage. And it's really sort of amazing that imitation learning purely worked so well. And this gave us a lot of hope because this agent that was seeded with basically all human experience in the game was able to perform perhaps at median human level. It's a gold to platinum level, which is 50% percentile of proficiency. And also, obviously, was also able to beat all the built-in AIs, which is great. So as a result of this, we decided, OK, let's start from imitation learning or supervised learning. We have all these community replays that create the very first agent. But then if you just run self-play, because StarCraft has so many different strategies and modes, it ends up having some attractors and areas where the policy would get stuck at refining one particular strategy, but not really exploring in strategic space. So we decided to go and again take inspiration for how humans have solved the game, which is by playing online, and every one of us could be playing with different preferences. Maybe I want to win quicker, maybe someone else likes this kind of unit because it's a cool spaceship, and so on and so forth. So we created a population of agents instead of a single agent doing self-play, playing each other all the time for 2 weeks, real time, which amounts, again, compute-wise, to 200 StarCraft 2 years. It's an interesting life, I'm sure, to play so much of StarCraft. But that actually made these agents refine all the strategies that they could bootstrap from human knowledge that they got from the imitation learning phase. And eventually, we chose an agent which was the Nash of this league, which, if you know what Nash is great. So that actually, at this point, we were not sure how good these agents were. We knew that it won against the best DeepMind player, which was a top 2% player in the world on Master. And we challenged 2 professional players that played a series of 11 games, actually. And we got pretty good results. The nice thing also is that this policy, much like the Go policy, was able to run on a single GPU. And to do an inference, to go from the image or the observation to the action, it took barely 30 milliseconds. And that was important because this is a real-time strategy game. You don't want to be pausing the game to think, hey, let me think what I'm going to do for 3 days and come back. I mean, you could, but that would be a pretty heavy handicap for the human. It would probably not be great to play like that, and we actually tried at the beginning, so I know this. So eventually, we saw some interesting behaviors and techniques and very good micromanagement skills of controlling units. And there's a very nice blog post that we write about that. This actually has sound, so I'm going to skip this. And just to summarize, we start from the supervised learning policy, which is perhaps at the median human level. And then with this Alpha Star League, we really bootstrap this process to levels of grandmaster play, which was really unprecedented in terms of how an agent that actually not only was an agent, but it didn't use any rule-based system. It was simply a neural network, transformer neural network with an LSTM and so on. So if you want to know about the architecture, come to talk to me later. It was very fun to develop, actually. So these agents were able to play well. So my last couple of minutes, I wanted to say, okay, so looking at these successes, what are the patterns for success? And there's really a lot of challenges ahead. What would those be for especially deep reinforcement learning? So let me list 4 properties, and we will start to understand how to actually tackle deep reinforcement learning, which perhaps is not the most interesting answer. But when deep reinforcement learning works is well, if your environment is full of rewards and there's not so many actions such that a random agent would stumble upon rewards, like there's apples on the ground and so on, then things seem to work, right? So Atari is a notable example of this, but Montezuma is a game where this actually is very hard because there's not many rewards, it's very sparse. Secondly is obviously if we have available human data, human demonstrations, and ideally at scale, then we also can bootstrap these and develop very good initial policies that we can then refine with reinforcement learning. Third is if there is any algorithmic bias, like search works so well for chess or for Go, that we can use again to kind of catapult the policy to be a little better, that's also great. And last but not least, you must be able to simulate many trajectories very fast, faster than real time. And with all these, what is kind of maybe the background signal here is that you must convert your deep reinforcement learning problem into supervised learning. And this really is not the only key component of success, but it feels like so far in DeepRL, we always need to rely on some form of supervision to some extent, which is fine, but obviously it's a challenge for the future. So what are the challenges ahead? I would say real-world problems are very challenging. Why? Because we don't have simulators of the real world. And probably to create a simulator of the real world is harder than to drive in the real world, right? So this is kind of problematic. We can do very cool things with DeepRL, but probably not solving real-world problems yet. Secondly, we would really like for transfer to work, to be able to claim we have general AI. So if we train AlphaGo to play Go, it should really learn to play chess quickly. In theory, it's much more simple. And similarly, AlphaStar playing StarCraft should really play Atari games trivially. These games are like from the 70s, the 80s, and I don't know, I never played these games, right? So, so anyways, but I would say this is not maybe a challenge for DeepRL. Let me give you another example. An ImageNet classifier should also be trivial to adapt to classify MNIST digits. And believe me, this is not trivial. You train state-of-the-art ImageNet, and it's quite difficult because it's different resolution, it's black and white, and so on. It really doesn't work, and this feels wrong. Why should we throw the weights? So what we do is we throw all the weights out. But the learning algorithms generalize, right? If we get a new data set, a new environment, sure, we restart the process, and we get to good policies or performance. But these networks are, by and large, thrown away, which doesn't sound right to me. And last but not least, the theory and understanding of deep reinforcement learning would be even harder, I would say, because not only there's non-convex nonlinear functions, but the loss is non-stationary, and you also have multi-agency. You have agents interacting with each other. So there's really a lot of theory to be worked on. And with that, I'm going to be thanking you for being great listeners, and I'm happy to discuss this later, or maybe one question we might have 38 seconds, according to this clock. Thanks.
Question?
So, thank you. Now, DeepMind has done many great pieces of work, AlphaGo, AlphaZero, AlphaStar. I recently read a paper, OpenGo, where they replicated or re-implemented the AlphaZero and they analyzed it. So my question is, what is DeepMind's attitude towards reproducible research where they don't release the code and some of the details?
So I think the answer is OpenGo showed that the research is reproducible, actually, because they read the paper and they reproduced the research. I think we shouldn't conflate, although they are related, open sourcing with reproducibility, right? I mean, I myself have experienced this repeatedly. For instance, the paper that was about machine translation, I would say, has been reproduced many times. Machine translation now is deployed. That paper, we didn't open source it either. So there's a discussion that is very interesting about open sourcing and about reproducibility, but I don't think there's an if and only if in both directions. That being said, open sourcing might help accelerate or build more on top of technology that is important. That I agree with. It's great that OpenGo did it, and we open source things, not everything. It's sometimes also very challenging and time-consuming, but I appreciate, of course, the comment. But I would say that precisely OpenGo showed that AlphaGo was reproducible, actually.
Hi.
Yeah. Hi.
Thank you for the lecture. It was great.
Thanks.
I'm sorry that my question is more technical, but
that's okay.
As you mentioned, not all the details are open. I know for Atari game that the input for the network was the whole image. What about Dota or StarCraft?
Yeah, so both in Dota and StarCraft, you get to see more a symbolic representation of the input. Dota, there's a nice blog post that describes it. In StarCraft, what we did is we took every unit that would be placed in a two-dimensional array, and instead of having these being seen as an image, we see it as a set of units. But actually, there's a very nice paper from FAIR, which is called Non-Local Neural Networks, which kind of transposes pixels as individual elements with XY coordinates attached to them, and then they apply a transformer on top, which is actually what we did for StarCraft. But yeah, I guess there's a lot of details. I'm happy to give you more details.
Okay, so would you say that the game or the machine had an advantage on the human?
Sure. Yeah, there's definitely advantages. Right. Even there's things called invisible units that are a bit hard to spot for humans, that the machine had basically a bit saying if the unit was invisible, and it obviously was hidden many things from properties from the units. But yeah, I would say in some work, the raw input doesn't really mean, you know, a camera, or we didn't also build a robotic arm to play StarCraft, right? So there's quite a few nuances in terms of being exactly playing like humans experience these games. So that's a very, very interesting conversation, actually.
Okay, thank you.
Thank you. Thanks.
Okay.